that lead to more stabilized species than just the primary, secondary, tertiary carbocations. And so here I'm going to specifically talk about carbocations that form that are resonance stabilized. One example of that is forming allylic carbocations. Okay, so here's an allylic carbocation. In this case, if I just have 3 carbons here, this shows this has an MZ of 41. And recognize, if you allow me to go back one more time, allylic carbocations, at least in this document right here, is significantly more stable than some of these other carbocations here. Okay, so if I can form an allylic carbocation, I'm going to do so. Okay. So how does allylic carbocations form? So they usually form obviously with a double bond. Okay. And so here is an example of an alkene. Okay. So recognize alkenes have 2 types of bonds. I either have sigma bonds or I have pi bonds. Again, based upon what I taught you guys on Thursday, we're going to pull off an electron off a pi bond. Let me just show that here for this terminal system here. So here's my double bond. Often books show this as a parentheses and then a radical cation. Instead, what I want you guys to do is show it in this fashion, where I basically show the pi bond and I show that I removed the electron from the double bond. And so now that I have a double bond that has a single electron, I'm going to show one of the carbons with a radical and the other carbon with a carbocation. Okay, so this depiction is this is a better depiction of what that is intended. All right. Now, what I also want you guys to point out here is that I'm using single arrowheads. So when I use single arrowheads, again, I'm breaking bonds homolytically, not heterolytically. Okay, so homolytically means that you're breaking a bond, you're breaking the bond where each atom is going to get an electron. Okay. So with that being said, now that I can basically see this electron, okay, I'm going to basically break this bond here. If this is the carbocation, if this is the carbon radical, this is the bond that's at the alpha carbon. Okay, I'm going to break this bond homolytically, where this bond, this electron to that bond, one of them goes to R, and the other one is actually going to go on to form a new double bond here. So if I take this electron, break it homolytically, I get this electron coming here, and I get this radical electron on the p orbital going here, and that consequently will form a resonance stabilized carbocation, in this case an allylic. Okay. This is an example of something we're going to talk a little bit more about, but this is an example of something called alpha cleavage. Alpha cleavage is one of the best methods of breaking bonds. And one of the things I'll point out to you guys, and one of the things I want you to recognize, every time I do alpha cleavage, I'm always using single arrowheads. Okay, so I'm always going to break a bond homolytically, just like here, and I'm always going to form a new pi bond in that system. Okay, so it's going to be basically, if I say alpha cleavage, you're going to definitely see just 3 arrows, and all 3 arrows are going to be single electron arrows. Okay, and in general, the point that I also want to point out to you guys here is if I do alpha cleavage, the reason they go very well is they often form a resonance stabilized carbocation. Okay, so this is one example of alpha cleavage in the case in the case of alkenes. Okay, later on I'm going to be talking about alpha cleavage in the case of carbonyl systems. So let's see if we see this type of system. Okay, so here's a little different molecule. This is 2-trans-hexene. Okay, so obviously the first thing I'm going to do with electron impact ionization is I'm going to pull one of these electrons off the double bond. So again, the double bond has 2 electrons. The electron impact ionization, we're going to make this pi bond a 1 electron species. Okay, now that I have it as a 1 electron species here, recognize that this is the alpha carbon. We're going to break this alpha beta carbon here homolytically. So if you permit me, this is going to be a carbocation here. I'm going to push this electron here, and this electron here. what I will get is ethyl radical plus this resonance stabilized carbocation. Now that there's 4 carbons here instead of the former that was 3, I will see a methyl allocation at 55. Notice that's where it shows up. Okay, so if you allow me, let me stop sharing. I'll try to do this one so you guys can see it. So let me write this down before I stop sharing. All right, so here I am. Okay. Apologize, my double bond is ugly, but nevertheless. So the first thing I do is I'm going to take this molecule and bombard it with electrons. What that's going to permit me to do is kick off one of those electrons off the pi bond. So now I have a pi bond that looks like this. Okay. Now one of these is going to have a positive. There's not going to be an electron there. And the other one's going to have the radical. Okay. Over here, I still have a CH2 group. And I have that. Okay. So I'm going to use my red pen here. All I'm going to be doing is breaking this bond here homolytically, which means I'm going to take this electron, push it over here, and I'm going to take this electron and push it there. Okay. Simultaneously, I'm going to be pushing the radical of the double bond onto here to form a new resonance stabilized carbocation. So all I basically did was
Dr. Marinas, can you zoom in when you're done?
Yeah, I will. Thank you.
Dr. Marinas, can you talk again so that your screen comes up?
Yes. Can you hear me? Is it coming back up?
Yeah.
All right. Is that better?
Yeah, thank you.
Okay. So what I basically did here is I'm taking this electron, the pi bond, and once I subject it into the ionization chamber, remember that's just a beam of electrons. That beam of electrons basically pulls off that one of the electrons off that pi bond to generate this radical cation. So this would be my M+1 radical peak. Okay. Now that I have that, one form of making one method of breaking this through a fragmentation is through this alpha cleavage mechanism, in which I'm going to break this alpha beta bond here, and I'm going to break it homolytically, which means I'm using basically 2 arrows here, where one of this electrons goes onto this carbon, and the other electron goes onto this other carbon. And this other electron that goes onto that other carbon, I've broken the bond, I formed the ethyl radical. Okay. On the other hand, I can place that double bond, that electron here. Okay, so since I have 2, remember all this is a conjugated system. Okay, and what that means is essentially, you know, what I have here is basically that. Okay.
Dr. Marinas, is
Yeah.
it okay? Is it okay if we show the p orbitals only when moving the single electrons around, or should we also keep them at the end product to show the conjugation?
So yes, you can show. That's your question. You can show
Yeah.
me directly to that.
Okay.
Okay. I'm only trying to remind students that this is a resonance stabilized system. What does that mean? That means we have basically 3 or more atoms that have p orbitals on them, and they're all collinear, right? So one of the requirements for resonance is that you have 3 or more atoms that have a p orbital, and the p orbitals have to be all collinear. Okay, parallel. Now, just like we showed before, I could have also shown this. Let me just do it for you. No, I can't do that. So what I was going to do here was I was going to see if I broke this bond, but again, this is I don't have no alpha beta bond here, so I can't break it in this fashion. Okay, so there's no way only way I could break this bond is that way. Okay.
Yeah, I was just thinking about that too. I was saying that it might produce a primary a methyl radical, but then I realized we don't have another carbon attached to it.
Right. So let me go back to screen share. Okay. So again, it leads to that. And so one of the things I'll share with you guys today is that I'll show some examples. Again, in my PowerPoint, I have one spectrum that we'll analyze. I just generated a additional problem set. I looked very carefully. Most textbooks don't have very good problem sets when it comes to mass spec. So in lieu of that, what I did is I'm giving you guys 3 problems to practice. Okay, so I looked at Sorrell. Sorrell's the problems in the book are terrible. I looked at some other sources.